This video is about even and odd functions. For our notes, we'll start with an algebraic definition, which is for all x in the domain of some function f of x, if f of negative x equals f of x, then the function is even. Secondly, if f of negative x equals negative f of x, then the function is odd. And so this simple algebraic definition will prove useful in trying to determine if functions are even or odd. But more than that, there also are some graphical implications. And so some graphical implications for symmetry involve the following. Even functions are symmetric about the y-axis. So one simple example of an even function would be the parabola y equals x squared, the parent function. And we can verify this graphically and algebraically by looking at the following points. If I plot the point 1, 1, that means that when x is 1, y is 1. But notice when x is negative 1, in other words, f of negative x, would provide the same output. So that's an illustration of this rule we've already listed, such that when f of negative x equals f of x, when you put the negative value in and get the exact same output as you would when you put the positive value in, then that matches the algebraic definition for an even function. But then visually, the symmetry exists about the y-axis. You'll notice if you were to fold this graph on the y-axis and flip one side over on the other, then the graph would land right on top of itself on the other side. That's called y-axis symmetry. Odd functions are symmetric about the origin. And so let's take a look at an example of one of these such functions like y equals x cubed. And you'll notice already visually it does not have the same y-axis symmetry like x squared does. Otherwise, this graph, when folded over the y-axis, would not land on itself. It would be missing or shifted over. So instead, when it has origin symmetry, that means really it's a couple different folds we need. We need first to fold it over the x-axis and then over the y-axis. So if you imagine this branch we have for the y equals x cubed function in quadrant 1, if we folded it first over the x-axis, it would turn out to be something like this now green curve I'm drawing if we were to fold it over. And then if we were to fold it over the y-axis following that, this green curve would be folded over and look something like what we're seeing as part of our actual graph. So origin symmetry really means two folds. It's a vertical and a horizontal fold happening at the same time. Let's try an example where we want to determine whether the function is even, odd, or maybe neither. And this time the functions are given in their algebraic definition. Well, if that's what we're given, it'll probably be useful to apply the algebraic definition, which is we're going to test out what f of negative x is. And by finding f of negative x, we're simply going to rewrite our original function, but instead of writing x, we're going to write blanks. So instead of x to the fourth, we have blank to the fourth minus 4 blank squared, matching the minus 4x squared. And then in each blank, we're going to put our input value of negative x. And then we're going to simplify this to see if it matches the original function or is the opposite of it or maybe neither. So let's see, if you have negative x to the fourth power, a negative in parentheses to the fourth power would become positive x to the fourth minus 4 times, and then same thing when you have negative x in parentheses but you're squaring it, it would be a positive x squared, which happens to match exactly the original function f of x. So when f of negative x turns out equal to f of x, that matches the definition, the algebraic definition for an even function. Let's look next at our second example, which is where f of x should be written as 3x cubed plus 2x squared plus 1. Again, we'll apply the same algebraic definition and first evaluate f of negative x. That will be 3 times negative x cubed plus 2 times negative x squared plus 1. And if I simplify this algebraically, notice when you have a negative value to an odd power, this becomes negative 3x cubed plus the middle term will be 2x squared because that negative value has an even power, and then plus 1. But notice this does not quite equal the original function as given because there's an extra negative sign in front of that first term, negative 3x cubed. And because of that, we cannot say that it's equal to f of x, which means it's certainly not even. Now, you might wonder if it's odd. Well, odd would mean the opposite of the original function, which would mean that all the signs have to be the opposite, but that's not the case either. Only the first one is the opposite. So we have to call this one neither. Neither odd nor even. We'll look at our third example here, which is f of x equals x plus 1 over x. And again, plug in negative x to get f of negative x equals negative x plus 1 over negative x. We're plugging in with blank parentheses just to be safe. This, when simplified, would be negative x. And then the plus 1 over negative x could be written as just minus 1 over x. But then if you look back at the original function, this new one has the opposite signs of the original one, and in fact all the signs are opposite, which means this is really negative f of x, and that meets the definition so that when f of negative x equals negative f of x, this would be an odd function.